Hello everybody and welcome to NDC Copenhagen. It's really nice to see the room jam-packed, so thank you all for attending. I'm here to talk about the 5 things that every developer should know about building mission-critical systems. Let's see if my clicker works. Yeah, it works. So, for one, I've been part of this when I get called in the middle of the night by PagerDuty, informing me that there's something wrong in the system. And the bad thing is, sometimes it wasn't even that important, so I get called out of bed for something that could really have waited for the next day. And I hope that each and every one of you will leave this room today with a bit of knowledge that you need to not have that happen to you very often. All right, so let me quickly introduce myself. My name is Loek Duys. I am from the Netherlands. I'm the proud owner of my own consultancy firm, and I have many years of expertise in building mission-critical software. What we will be doing today is start at the basics and generally gradually flowing into more and more complicated scenarios. In the past year, I've been working in a bank project, and I decided to take this bank project as my example of today. And it's a seemingly very simple system. So you have a mobile device, and the mobile device is has a bank app on it. And that bank app, it will talk to the payment API. The payment API is the consumer-facing part of the system. So you take out your phone, you make a payment, it arrives on this API. Then the API will talk to the core banking system. And this is the system that holds the accounts and the balances, and the system that is able to talk to other banks in order to do payments. And then, for example, you can do a payment with another bank. You debit your local account with 500 euros, send back the OK, and it arrives back at the mobile device. So, relatively simple system. And now let's see how we can change this system into a mission-critical system. And you might be surprised what that involves. Right, so let's start off very simple with a server error within the core bank. So, same situation as before. You want to make a payment. Payment API calls the core bank, but somehow there's an issue and the booking cannot be made. So, the core bank responds to the payment API. Sorry, you're out of luck, no deal. And then the only thing the payment API can do is return back to the mobile device. Sorry, there was an issue. Well, you don't want that, of course. So the first thing to do here is to say, well, why don't we just retry this operation? And that would look a little like this. So again, same situation, you do a payment, it meets up at the core bank returns an error, but instead of returning the error immediately back to the end user, the payment API itself does another attempt, so it does a retry. And maybe, in the meantime, the core bank has recovered from that issue. It could have been a concurrency issue, like a deadlock or something in its database. So there is a chance that the second attempt will work, and then it reports back green all the way to the end user. And the end user, it did have to wait a little bit of extra time, but at least their payment was done. So, retry. It sounds like a very simple thing, but there's a catch. So, to summarize, retry is very useful if you are calling downstream services and they may have outages. So, simply have the client retry the request. Catch one is that this only works for transient errors. So a transient error means that over time it will go away by itself. So it could be that deadlock I was talking about. It could be that the server is temporarily overloaded for a bit. Stuff like that. Of course, a retry is useless if that error that you got back is you are not authorized to do this, or you have sent me a malformed request. You can retry all you want, but that will never work, right? The result of adding retry is that your requests to the core bank, they have a higher percentage of success. So your amount of support calls will likely go down. The price you have to pay is, one, your end users will have to wait a little longer, and two, which is actually more important, is that the downstream service, it must be aware that retry is even a case. Let me explain why. So, imagine there is a hiccup in command execution, and you want to do the same as before. You want to make a payment. The core bank actually works, so it does the booking, but on the way back, the answer gets lost somewhere on the network. So the payment API, it decides after a timeout, well, let me retry this operation, and lo and behold, maybe you pay twice. And this is what I mean, that the core bank needs to be aware of retry. This is a scenario we absolutely don't want, of course. All right, how to fix that? Well, this is when we will talk about idempotent services. And this is like the traffic light. If you hit it once, it will go green. If you hit it twice, it will still go green once. So, instead of just sending over a request, we add a little bit of information, and I mark that as an idempotency key. And it doesn't have to actually have that name, but it is a unique identifier that you send with your command to the core bank, so it can recognize that individual command. So if the same thing happens as before, so the response gets lost on the network somewhere, the payment API does a retry, but now the core bank can recognize the idempotency key and say, hey, I already processed this payment, so I will not do a double booking. A relatively simple solution to get a system in which retry is fully supported. To quickly sum up, if you have the need for retry, then also you have probably got the need for commands to be executed exactly once. The solution is to add a little bit of extra information to each command, uniquely identifying it, so the server can store that identifying information and compare it with incoming requests. The result would be that commands are executed only once, retry is safe, and you get a few problems in return. So now you need to start storing those idempotency keys. And of course your client needs to be aware that it should send this idempotency key. So two things that need to be in place. So key takeaway one here is that if you do retry more than once, make sure that the receiver is idempotent. All right, so retrying is nice, but what if the core bank system is offline altogether? Then retrying every request, that could quickly lead to very many unhappy users. Let me explain why. So the user wants to do a payment. The payment API sends it to the core bank. It waits, but the core bank is offline, and it will never return. So you do another retry, it waits and waits again. And in the meanwhile, the end user is watching his phone and asking himself, do I need to get another bank? So this is where the circuit breaker pattern comes in. So this can be a very useful pattern to resolve this initial problem. So same situation as before. You want to do a payment, but then if you zoom in to the payment API, which now has a circuit breaker inside of it, and then whenever it wants to do an HTTP request over the network, it first needs to go through the circuit breaker policy, then it will go through the retry policy, and then it will end up at the core bank. So the request flows all the way through. It has a timeout, it retries and retries again. And at some point, the retry policy says, this will never work. So back to you, circuit breaker. And it can then respond to that by going from the closed state, in which it is now, to the open state. And it's just like the circuit breaker in your home. If you open it up, the circuit is broken and requests can no longer flow through. And of course you can return that error back to the user. But you may wonder now, okay, but what good is this for that user? Well, this user is still out of luck, but another user wanting to do a similar payment, they will now talk to a similar HTTP client. the request will be blocked by the circuit breaker and then immediately returns. So this user at least doesn't have to wait forever to know that there is something wrong in the system. So they get their feedback really early. So if you zoom in to the circuit breaker itself, it has a little difference with the circuit breaker in your house. So in its closed state, the requests will flow through unhindered. But if there are issues, it will open up. So requests are blocked and the users get their feedback really fast. And then a waiting period happens. So after some time, this circuit breaker, it will go to the half open state. And that means that a few requests will flow through and they will arrive at the core bank. And of course, if that is still offline, it gets back failures. And that means the retry policy will open up the circuit breaker again. But if it does work, that means that the core bank is now back alive. So that means that the circuit breaker can be reverted to the closed state, closing the circuit again, and the messages can start flowing through again. So this is auto-healing at work. So if you have a retry policy in place and you don't want your users to wait forever for retries to fail if there's a downstream issue, you add a circuit breaker. The circuit breaker will detect downstream outages and give the users early feedback. So some users may wait to trigger the circuit breaker, while others, they get the benefit of early feedback. Well, there are, again, two prices you need to pay. One is, these are tightly coupled services now. So the availability of the payment API is directly connected to the availability of the core bank API. Not a good thing. And on top of that, if the circuit breaker does close back up, all of those payments that were stacked up, they now can overflood the core bank API. So, and we will cover both of them in a little bit. So the first thing to decouple those services from each other is by introducing something called the outbox pattern. And it's a name that was stolen from years ago when we were still doing paper mail. You had an outbox for messages that needed to be sent to other departments or other addresses. So if you add an outbox to the payment API, it looks a little bit like this. So we are now zoomed into the payment API. So it will still have an API endpoint, and payment commands will come in. But instead of immediately calling the core bank API, instead you put the message that you intend to send to the core bank, you put it in an outbox. And the nice thing is you can combine this into one transaction with your other local state changes. So if you need to update the local balance, you combine that into one transaction with the outbox message. And then, of course, you need to start worrying about the processing of that message, and you need to return something to your end user. So the return here is quite immediate. So instead of processing the whole downstream payment process, you just say, okay, I got your command, I've executed it, I have a message for the core bank to update my bookings, I've made my local changes, and now I am good to go. So you return back the 202 accepted to the caller, and then you can start processing. The nice thing, of course, by putting it in the outbox, that means that you can even survive crashes. So if my system now crashes, it doesn't matter, I can just start it back up again because my data is safe in my database. Now, for background processing, you need to have something monitoring your outbox and start actually sending these messages to the core bank API. So you can run a background job for that. And the nice thing is, even if the core bank API is offline, that doesn't matter because it can just retry and retry and retry forever because nobody's actually waiting for this call to complete. So offline, not a problem. So now you have a decoupled system and guaranteed delivery of messages. So quickly sum up. Retry can be well, a little bit boring for end users to wait for. So why not just store stuff in an outbox instead of processing immediately? that means that outbound messages will never be lost and you are independent of downstream availability. Of course, this introduces two new problems, and this is a pattern that will flow through the entire presentation. Async processing, because you have this background processor that needs to do its job, and that makes it very hard to see what's actually going on within the system. And background processing itself also has challenges in terms of availability, scalability, and ordering. These will both be covered. So, key learning point here. Yeah?
There's also a problem here that in case that the background bank service would say, no, you don't have the funds available, then we've already accepted
Yeah, that's true. That is true. So if the amount of money on the remote account is not sufficient, then you need a way back. But yeah, that's true. In order to not get me too much out of the flow, please can we do questions at the end, and then I will make sure to come back to this. But then you have heard the entire story, so problems will be solved likely. Right. So the key takeaway number 2 is services availability should not depend on downstream services availability. So you can counteract this with the outbox pattern. It's not always an option for logging in with your IDP. That's not an option, of course. You can say log me in and it'll be fine. So use this wisely. All right, so we have this background processing. We have a distributed system. How can we get a clear picture of what's going on? I thought I would start with an example in which my observability could lie to me. So my API, it has a health endpoint and it returns 200 OK. So it's ready to accept messages, even though payments are not being processed. So what could be wrong here is that my outbox processor, it crashed. So I can still accept incoming payment requests. They are still going into my outbox, but they are never sent to the core bank. And if I were to use only logging, then this would be really hard to find. So instead of only capturing logging information, I suggest you also add end-to-end tracing, meaning that you can follow a payment request all the way from the mobile device to the core bank and back again. And on top of that, adding metrics. So you could have metrics in your system that say the amount of transactions processed per second, or maybe even the depth of my outbox. And these could be metrics that you can use later on to trigger alerts on. So in order to get complete insights into your payment process, I suggest you add logs, traces, and metrics. Be aware, though, that all this information that could increase your cost of processing. All right, but how do you do that? So how can I add all this telemetry to my application? Well, my solution here, it's not the only one, but I do recommend this one. It's using OpenTelemetry. So it will have features for you that you can use logging, traces, and metrics within your source code. And the only thing that you, as a developer, need to do is to make sure that this works across boundaries. So whenever you put some work away in an outbox queue, you need to make sure that it captures the telemetry context. So trace ID in this case. And having the trace ID means that you can rehydrate the trace when executing the background job, when crossing network boundaries, etc. And this will give you a really nice end-to-end view. Right. Don't just take my word for this, because I've actually got this running. And don't worry, I will share this, the source code of the project with you all later. So here you can see an actual trace from a payment request that was done on my demo app. What you can see is it started with an HTTP call on my API. Then it was put inside the database, where it was picked up by my outbox processor. The outbox processor, it first did an account validation. Do we have enough funds in place? Do we have this account? Is it one of ours? You could argue you could put the validation before the enqueuing of the command. There are pros and cons of doing it in two places. A little bit out of scope. But next step would be to actually process the transaction with the core bank and update the database over there. So this already gives you an end-to-end overview. And if I were to, toggle all these boxes, you would see a lot more stuff. But for now, this is fine. Right. So be aware that silent crashes in your distributed system, they may hide issues. If you add proper tracing, end-to-end tracing across service boundaries, and you combine that with metrics and alerts, then you should at least have some visibility within your system. All right, so let's circle back to that outbox processing for a bit. So, of course, it introduces all kinds of new problems. For example, that crashing outbox processor I was talking about. So if I have only one outbox processor and it dies, processing stops and no messages will flow through to the core bank. Well, you say that's easy, you just add two outbox processors and then all your problems are solved, because if one dies, the other one can still do the work. Well, you guessed it, this introduces more problems. What if we have two outbox processors? They are concurrently working on this outbox. So this is the first record to be picked up. If you are not careful, they may both pick up the same task. So what happens if outbox processor 1 and outbox processor 2 both try to deal with the first record in the outbox? That's probably something that you don't want, because you will get maybe two accounts. And it's not very useful either, of course. Another problem is timing. So if you say, now I got this first problem solved, they will execute separate commands, then it can still happen that because I am trying to create account X here and then update it as the next step, what if the create takes longer than the update? So the create is still running here, but it was processed by processor 1. 2 picks up the second item from the outbox and then it tries to update the account, but it doesn't exist yet. So also a problem. Fortunately, there's a solution here as well, and this is called leader election. And leader election means that you have two outbox processors, for example. They will both start racing for a lock in a shared lock store. So they share a lock store. And because it's a race, one will win. In this case, the outbox processor 1 gets the lock, and that makes it the designated leader, and only processor 1 is allowed to process records from the outbox. Well, you can see a scalability issue there, right? So if you have one leader, it won't scale very well. So it can only process as fast as it can, and it is, well, generally it would be better if you have multiple processors running side by side. Well, this problem also has been solved, and that is partitioning. So instead of having one lock available, why not have a whole bunch of locks available? And as long as each partition contains information that will never conflict with other information, so in this case, operations are partitioned by account ID. So operations on one account will be separate from operations on another account. So these are safe to run concurrently. So it's just a matter of racing for locks again. In this case, 2 locks were distributed, each has 1, and that means that the processor 1 can process partition 0, and processor 2 can process partition 1. And they will never interfere because it's about totally different accounts. Right, so if you have a background worker, then also add leader election and preferably include partitioning in order to have a very scalable, ordered execution. Right, and then there's the problem of the circuit breaker coming back online, or maybe the core bank recovering after an outage. Well, we nicely implemented the outbox, of course, so we have many requests in many instances of the payment API up and running and waiting for this core bank to come alive. So it becomes green again, circuit breakers flip back on, and the payment APIs, they start overloading the core bank, making it buckle and fail immediately after. So this is a situation, also it has happened in real life, and that's something that you really don't want, because it will never resolve itself, of course. So the trick here is to add something very similar to an outbox. It's called an inbox inside the core bank API. So instead of inside the core bank API immediately executing commands, why not say, okay, I have received your command, I'll put it in an inbox, and as soon as it's in the inbox, it's durable, it can survive crashes. You can say return 202 accepted. I've received your command. I will promise to execute it at some point. And then, of course, what you end up with is a whole list of commands you need to execute. So you need an inbox processor as well. So a background worker that will process all these things and execute the commands one by one until they succeed. So what you end up with is a system in which the outbox works together with inbox. So core bank becomes alive again. It starts hammering with outbox requests. They flow to the core bank API. They become inbox commands. And now, instead of being forced to process everything immediately, you have this nice queue of work to be ready to be processed. So now the core bank can process these items in its own time. And there's a nice extra benefit here. So if we quickly circle back to idempotent services, this is actually the way to do this. So imagine you have an outbox, and it has a record, and it has an idempotency key as well. So you send it to the core bank, where it ends up in the inbox, and it has the same idempotency key. So if there's an issue on the wire back, payment API retries, and it says, hey, I already have this one, so thank you, I will do nothing new. So 202 accepted here, and everything is good to go. So you now have guaranteed delivery of messages and also guaranteed execution of commands. Right, and this will be a little bit of an abstract demo here. So I have my system up and running. So my whole core bank, it runs on my machine as we speak. And I can now talk to the core bank and say, well, this is my idempotency key. I've named it transaction ID here. And this is the unique identifier for each payment command. So when I talk to the core bank, the first time I send this request, it says 202 accepted. This is the transaction ID I received. The status is pending, and thank you for calling. So no results here, of course. And then if I send it a second time, you can see the status has transformed into completed, and that means that core bank says, you know, I received this command before, it was executed, and thanks for calling. But it doesn't do a second booking here. And the cool thing is I can do that as often as I want, and it doesn't change a thing. So if we now go to the live statistics, let's see. This may or may not work, but it is a cool demo if it works. Let's see. Right. Now that's the demo guard for you, I suppose. All right. So what should have happened was you see one trace that looks a lot like the one I showed before. Let's see.
Select a different service. I think you talk directly to the core bank API.
Oh, you may be right there. Thank you. Oh, that's actually a really good one. Core bank obviously has some idempotency detection, but the payment API has the same. So thank you. That is very helpful. Let's see, I should now have a trace. Yeah, so this is the processing of the payment. It has 60 spans, and they cover everything from outbox to inbox to something I haven't even talked about in terms of messaging. So really end-to-end flow. And if I now send the same request again, it will say, oh, 202 accepted. So the state on the payment API is still the same. But if I go back here and get more traces, you should not see 60. Let me try it again. You should not see, oh, wait, sorry, I should have sent this one. Right, so you should not see 60 traces, but you see 4. So now it says, I will stop at the payment API because I've seen this record before. Everything is well, it was processed by the backend, and I don't need to bother you with my errors. So this was a successful call, 202 was returned, but internally the payment was not processed. Sorry, that was a little bit of a messy demo. All right, so I've been talking about REST calls, doing REST calls between services the whole time. But the cool thing is the outbox and the inbox pattern work just as well for messaging. So imagine you have a way back and maybe a payment that was done by the core bank, it didn't work, or maybe it did, and you want to inform the payment API. So you don't want to have the payment API constantly polling. So a really clean way of doing this is by sending a message back. And the outbox can be used here to say, okay, I want to send a message to recipients. This is pub sub, so I want to publish a message. So I will put it in the outbox, and then my outbox processor, it will continuously try to put that message in my message broker. That could be Service Bus or RabbitMQ locally, whatever you please. So as soon as the message broker says, okay, I've accepted your message, then it can be marked as completed in the core bank API outbox. And then at some point it will end up on the payment API because it subscribes to those events. And then it can say, okay, so I will make a command in my inbox saying I need to update the balance based on the information from that message. And then even if the receipt back to the message broker fails, message broker may say, okay, here's that message again because you failed the last time. It can say, you know, I've already received this message. I already have a command in my queue with the same idempotency key. So thanks anyway, mark this message as completed. So inbox, outbox, it doesn't have to be correlated to REST calls. It can also work very well with messaging. Right, so if you combine all of this within your system, you get an outbox for guaranteed delivery of messages to remote systems. You get retry to deal with transient errors. You get a circuit breaker when transient errors just won't go away. You have an inbox for buffering inbound commands, so you can deal with surges and also guarantee processing. You have leader election to make sure that even though you have this whole list of work waiting for you, it will be processed in the right order and at exactly once. So together this means by introducing these patterns in your services, you get loosely coupled, resilient services that guarantee single execution of every payment. Kind of nice. So we added a lot of complexity now. So even though it's two very simple APIs, if you build this all in, then you may wonder, okay, how do I know for sure that everything works? Well, I spent some time working on that as well. So what you probably want is some kind of automated resilience testing. And in a banking scenario, you have really tight regulations about high availability. So your system, it pretty much needs to be up 24/7. In case of emergency, it needs to be recovered really quickly. But how can we do that without first deploying it in production and then just waiting for stuff to go wrong? Well, you can deal with a lot of these challenges locally already. So on your dev machine, you can do a lot of stuff that will help you deploy to production with more confidence. So what you can do, for example, is add faults during the test. So you can test locally and have some system in place, a proxy server that injects faults into the system. So you can try to see if your retry behavior works. And if that works, then you know at least that you have resilient software that you can confidently deploy. But again, you do need a way to introduce this chaos, and preferably you want to have this automated, so any team member can simply hit F5 and then have it running on their machine, and then they can do these resilience tests themselves locally. So the way to do this, or I should say a way to do this, is by adding a proxy server between the APIs. So instead of talking directly from payment to core bank, it flows through a proxy server. And this is not just any proxy server, this is a tailored product, for example, a dev proxy. And what it can do for you is fault injection. So in this case, you see a payment request being made, and the proxy server, it determines, okay, let's inject an error here. And then for the next request, it says, okay, you are allowed to pass through. And the cool thing is, these proxy servers, they can be also used to record calls. So if you're in a situation where you have an identity provider, and you need to log in first, and then you can call these downstream APIs. The proxy server can record those calls and then mock the IDP API. So you take it out of the system. So instead of having to go through the identity provider to get a token, you can say, no, proxy server, you mock these calls for me, and always return this hard-coded token. And that gives you the opportunity to get it out of your load testing later, and focus on your own software. And that brings us to stress testing. So first we did resilience testing, and now we are doing load testing. So again, in a banking environment, the regulations are kind of strict. So you need to follow strict rules about performance. Payments need to be processed in X time. And a way to make sure that this happens is, of course, by running multiple instances of every service. So you can spread the load a little. Of course, if you have an inbox and an outbox, you also need a leader election to make sure that operations flow smoothly. And an even better way would be to add multiple data centers to your architecture. So you can distribute your compute across 2 individual regions that don't have any dependencies to each other. And my recommendation in that case is that you also consider running active-active. So the secondary location, it should not be standby, but it should be up and running at any time. So you can really use those CPUs and have them work for you. Of course, that also means that you need to deal with your data. And then data, it has a tendency to be in one place. So you need to make sure that data is also copied in some way. And most cloud services nowadays, they will have these features for you. But if you're running on-prem, then you probably need some kind of a storage area network with synchronization in between. So the end result here is that you are tolerant to data center level failures, and you do not ever have to do any failover in terms of compute. So for data, you may still need to have an active master database. That's fine, but at least for compute, you are always running active-active. Right, and then of course that begs the question, how do you do local load testing? Well, who here knows Aspire? Not everyone, but at least half. All right, I'll quickly explain what Aspire does. So Aspire is a really nice way to orchestrate processes on my local dev machine. So Aspire, I can use it with a CLI and say, this is my recipe of my application. It has an API, it has a proxy, it has databases. And now you go and run these for me and make sure that they are up and running and ready to go in the right order. So the way to do this with my demo app, that would be to first start up the core bank API. It will just be launched with its data store dependency. And then optionally, I can add my dev proxy to it to introduce faults during my load test. So you get both resilience and load test in one go. Again, the payment API, it needs to be launched normally, but it may have a proxy configured pointing to my dev proxy. And then I choose to use K6 a lot for load testing. K6 is a Grafana product. It's open source, free to use, so it's really wonderful. Make sure you have a look at it if you haven't yet. And then I can fire up these load tests and they will start hammering my payment API and I should be good to go. All right, so you can, in fact, run local tests in a very automated way by running K6 and all your dependencies using Aspire. So the main trick here is that you discover any issues before going into production. And this is not just a story. This is actually something we do at the bank. I've done these performance tests on my machine, and I found out, for example, that we were using a SOAP client, and it had cached like a couple of megabytes of XML schemas inside, and we were using it with dependency injection transient, so that means it was created and then disposed again for every request, while we should have used it singleton. So it was doing all that caching for every request that came in, and one request was fine, so we tested locally with one request and it was unnoticeable. But if we did 100 requests in parallel, all of a sudden it buckled. And it was something I found out on my local dev machine instead of being called in the middle of the night. Right. Of course, nowadays all good talks have a little bit of AI in it, so I thought, well, let's add a little bit here. But not go all the way over the top, but you know, just as an idea, we've added an orchestrator for our automated load test as well. So the way this works would be to run these load tests and then wait for execution. Remember, I was talking about eventual consistency, so I have all these inboxes and outboxes, background processing. So simply firing 1,000 requests to my payment API, that's not enough. That will be done in maybe a second or something. What I want is my load test to actually wait until all these inboxes and outboxes are empty and all my transactions have been processed. And additionally, I would like to have some kind of a clue about their correctness. So this is why I invented the load test support API. And this is code that runs side by side with my actual code, but it will never be deployed to production. It only runs on my local dev box. So this is an API that has direct access to my databases, and you can query it to see, you know, is my inbox empty? Is my outbox empty? So a really convenient API, never to be deployed to production. So I took it separately. And then I want to do some assertions. So is my load test complete? What does Grafana K6 say in terms of for performance, etc.? Were there any requests that took an abnormally long time? And you can ask all these questions to various MCPs. So my load test API, it also has an MCP for agents to talk to. So it can ask, hey, was this test performed correctly? I have an open telemetry MCP that talks to my Jaeger. So the telemetry, the trace view I showed you earlier, that's also accessible through an MCP. So my agent can say, hey, were there any requests that took an abnormally long amount of time? And if so, which one? And if so, can you get some error logs from the Aspire MCP so I have a clear picture about what's going on? Right, and then of course I can analyze all this information again by querying the Aspire MCP and the OpenTelemetry MCP. I can slice and dice all my telemetry, and I don't have to do it myself because I have well, Copilot who is much better at that sort of stuff. Right, let's do a quick demo about that as well, and this will be a text-only demo, so it cost me about $3 every time I run this. So yeah, that's the downside, of course, of the token-based approach here. So what I do is I have created a skill that says, you know, this is my load test skill, and it has these steps in it. So at first, it runs my app host. So step 1, start the app host. Is this readable in the back as well? Not so much. I can zoom in. Better? Okay. All right. So the first step is to run my regular app host. So this is my APIs and optional proxy. And then the second step is to add an additional load test app host. So a second Aspire project that runs case 6 for me, and my load test support API that has a direct connection to my databases. Then obviously we need to wait for everything to start up. So it waits until the load test support is healthy, meaning that everything is good to go. Then it talks to my load test support MCP, which is not always there. It's only there once my load test support app host is starting. So it needs to discover it as we go. And then say, okay, well, I now have a session ID. That means a conversation with this MCP. I can ask questions later. So we are all good to go. Then I need to wait until Grafana says I am done, and to wait until my load test support API says I'm done. So it will poll for a couple of times, asking, you know, is my inbox empty, is my outbox empty, etc. Then it says, okay, 100% of my transactions have processed, and then it's time for assertions. But first, let me switch to this tab here. The way I do all this is by exposing my load test MCP, of course. So if you don't know MCPs yet, it's just an API that my agents can talk to, and it has a bunch of operations that have really elaborate descriptions and some intelligence around it. So reset my database, that's a task to reset my whole test scenario and seed some data in it. Then poll until drained means, of course, wait until my inboxes and outboxes are all empty, and that we have the expected amount of transactions, which is a variable. And then what happens is I can just query my database here. So this is not an LLM doing all the hard work. This is just code doing the hard work, and the LLM gets the results back. Then I build up a whole response saying, okay, inbox is empty, outbox is empty, etc., etc. This many have failed, this many have succeeded. And then I can do the same thing about correctness. So in this case, I decided, well, let's also add some checks on the balances. So after my load test, I wanted all the balances to be the same as before, because I first transfer money out and then transfer it back in, and then the net results should be 0. And I can then ask my model, you know, get these assertion results and give me a nice report. And that's what you see happening here. So it correlates with all the traces, and then no errors, all is looking good. Scrolling down, and this is my report. So it says all my tests were green, the inbox, outbox are empty. I do send a couple of duplicates. So I do the same commands multiple times, but the system should be resilient to that. The balance is as expected, and everything matches. Then it flows on to the trace analysis. So it has talked to Jaeger to see if there were any outliers in performance. Well, it says, you know, there are no slow requests. So in this case, this is all green. And of course, if I now say I want it not all green, what I should do is, of course, go to my load test and say, oh, sorry. Load test support. Yeah, here we go. All right, so what I can now do is go to my app host and say, you know, when I want to run my dev proxy, I want to increase the amount of errors. So when I do a load test, it also tests for resilience. So you could go all the way to, you know, from 5% of all requests failing to 95% of the requests failing. And then you will see your load test will take forever because it retries and retries and retries. And after a few days, it will be done. But, well, obviously this is a tell-only demo. I'm not going to bore you with that. So this is a really nice way to combine my resilience testing with my load testing, all using standardized tools and a little bit of Aspire and LLM magic around it. Right. Another thing I did was create first a dev container. Show of hands, maybe who knows what dev container is? Oh, not too many. Okay. So dev container is really a way to specify my development environment as a JSON file. So I can even show it if you want. Dev container. So this is my dev container JSON file, and nowadays it's a very common standard, and it says, take a base image, it's a Docker or container image, and on top of that mount a couple of directories on my host, add a few VS Code extensions to it, and expose a few ports, and maybe if you're done, do a little bit of post-creation scripts, in which I do stuff like install all the necessary tools I want, like the Aspire CLI, dev proxy, Dapr, which also you use within my code. And I do a little bit of magic with certificates. I won't bore you with that. So what I did here was create a file to define my development environment. And that means that anybody who pulls this repo, they should be able to open this dev container. Most IDEs nowadays support it. And they will have a development environment that is configured as exactly the same as my environment. So that means that you can pull it, run the dev container, hit F5, and you are up and running. And if you go one step beyond that, you can also say, well, now I want to run this in the cloud. And this is always a little bit magic, but now I take my dev container, consider it VS Code in the cloud, pre-configure it with every pre-requirement I need. And if the demo guards are willing today, this should now pop up a development environment within GitHub. Right. I do not seem to have a lot of luck with... let me see. No. Yeah, retry. Maybe it works the second try. So while it tries again, a development environment in the cloud based on my dev container spec. So that means anyone who pulls my repo, they can run it. And now if I also make use of this development environment in the cloud, the only thing I need to run my project is a modern browser. So all the rest is taken care of. So this is a GitHub feature. If you haven't used it, well, please do, because it's a really nice feature. And this means for any demo project or real project, you can just say, okay, let's add a CodeSpace and a dev container. And then anybody joining the team, they clone the repo, start a container based on that repo, or a CodeSpace based on that repo, and they're good to go. And now I'm opening my CodeSpace within my VS Code. I can also just use it straight from a browser. So anybody can work at any time. You can do it in the train. You don't need like a heavy-duty laptop. And everybody's development environment will follow exactly the same install, making it a really nice way to onboard new team members. All right, so as you can see, this is just VS Code, so it's nothing fancy here. I just wanted to show you that it works. And then if it's up and running, it should also... let's see. Maybe it even runs. You know what? I will skip that. So I could just hit F5 in that dev environment, and then everything will work equally well over there. And well, it would look something like this with the Dapr dashboard and pgadmin for direct database access and all these tools I have available. So quick and easy. All right, so I won't go over all these again, but this is like the summary of all the 5 key learning points I believe anybody should know when walking out of here. right? And of course, I promise to share all the links with you. And nowadays, it's very popular to use QR codes, but also, if you want, you can type the link. There's nothing in between. Feel free to steal my code, connect on LinkedIn if you want the slides, or just connect if you want to. And if you need any help implementing any of this, well, you know where to find me. With that, we have about 5 minutes left for questions. I promise to get back to at least you in front. So you were asking, like, if you have an account that wants to do payment and you say 202 accepted, that could be a bad thing. So it can always be a bad thing. So what you can do is, before you accept the command, validate sufficient amount is present on the account. Do it again during the execution of the command, because stuff may have changed in the meanwhile. And by using that messaging, the pops up messaging, you can report back to the end user or the caller, I accepted your payment before, but something went wrong and we need to deal with that. So that's it becomes a business case instead of a technical thing. Make sense? Yeah. Somewhat? Okay. And yeah, you in the back?
Yeah, well, what about the status back to the client? When they submit the payment and you put them into your inbox or outbox, so you put the status back in progress, or have you added any extra statuses and inform the client about the process of the payment?
Yeah, so I would generally, to report back information to the caller, I would generally opt for an API that exposes the state. So if you return 202 accepted, you usually return an additional bit of information for the client to go and get more information. So you don't just get 202 back, but you get an endpoint that you can get and get the status of that pending request. So this is the clean way to do it. And on top of that, if it's already processed and the request was done, then you have this messaging channel to report back any issues, maybe. Make sense?
Yeah, and when the payment just picked up but hasn't been sent to the core bank, you just give back the status in progress?
Yeah. Yeah, this is what I call pending in my system. So as long as it's not processed, it's pending. And then once it is processed or being processed, it's pending. And then when it's done, it's completed. Yep. Yep.
I have a question in the context of instant mobile payments, which are quite common nowadays in Sweden on the other side of the bridge.
Yeah.
There is a very strong expectation that if I see 200 successful in the user interface, like this transaction made all the way to like the national bank, Riksbank, and that yes, money got transferred from my bank to the other bank and from my account in my bank to
Yeah.
the other account. Does any of this then apply in that case, or essentially, yeah, you need to freaking just show the user a fader somewhere around the call chain between your bank, between your mobile app, between Riksbank, and stuff has happened. Sorry.
Correct. Yeah, so my story, it holds up because I was doing like SEPA scheduled payments, and then it all is fine if it happens somewhere during the business day. But for instant payments, retry I would use, circuit breaker probably also, but inbox, outbox in that situation, in that business case, will not work, because what you say is true. You need to go all the way to the other bank to get confirmation. We have a dedicated connection for that. And only if we get back the answer from the downstream bank, then we say this instant payment has completed. Yeah.
But still be useful to show the trace ID to the user so that it can investigate at least in case it needs support.
Yeah, that's true. Yeah. Also return that trace ID in the response for support purposes. That's true.
Thank you.
Yeah, welcome.
My organization, the lines would be, we're not doing this from the ground up.
Mm-hmm.
I wonder why you don't reach service plus another service plus similar to production system. This is very hard to track.
I'm sorry, could you please speak a little louder? It's hard.
I'm saying, in my organization, the advice would be not to do this the ground up. It's very complicated to get right in a production system.
Mm-hmm.
So the advice would be to go with Service Plus or Kafka or something like that. And there's no mention of those problems or similar problems. Do you have some words on that?
All right, so I will admit that this introduces a lot of complexity. I warned ahead of time and after time, so I think that's true. I did mention Service Bus for the pops up messaging back to the front end. Like if you do decoupled system, then inbox outbox will work equally well for doing REST calls and messaging calls. I wouldn't say like putting a message on Service Bus resolves all the problems that I mentioned. All right, so maybe we can take this one offline because it feels like it needs a little bit more clarification. Hmm. All right, all right. I'll think about it for a bit. Uh, thank you. More questions, maybe? Yeah.
Do you have any regression tests on performance metrics?
Yes. So case 6, it emits a report, and you can save that report by attaching a volume, and then over time you can ask it to well, save many reports. And as long as you keep saving that data, you can ask an LLM to compare, or do it the old school way. But for sure, yeah, these performance degradations over time, that's really something you would want to know about. And you can also measure the impact of your pull request on the performance of the yesterday. So yes, please keep that information and store it as if it's gold. So, okay, if there are no more questions, then I would really like to thank you all for staying with me, and hope to see you again next time.